Okay, let's recall what the elementary row operations were first. There were three of them. It doesn't matter what order I list them in, but okay, one of them was where we can switch two rows of a matrix. Another was replace a row by adding to it a constant times another row. And then finally, multiply a row by a non-zero constant. And in this section, we're going to form what's called an elementary matrix associated to any one of these elementary row operations. And the way we do that is as follows. We take the m by m identity matrix for some integer m, and that's just the matrix with ones along the diagonals, zeros elsewhere, so we don't write all the zeros that are hidden over here. And then we perform the corresponding elementary row operation, whichever one we choose, on this identity matrix, and then we get a new matrix. But let's look at an example. First, let's fix m equals to 3. So we're talking about 3 by 3 matrices. And here's the identity matrix of size 3 with ones along the diagonal and zeros elsewhere. And so let's first consider the elementary row operation that switches the first two rows. And so what we do is we take the first two rows of the identity matrix and switch them. So we get this. We're going to call this an elementary matrix associated or corresponding to switching the first two rows. Now let's consider another example of an elementary row operation. Namely, we can take or replace row 2 by row 2 plus 6 times row 3. So that's an elementary row operation. And what we want to do is do that row operation to the 3 by 3 identity matrix. So here's the 3 by 3 identity matrix, and we're going to replace row 2. And the other rows are going to stay the same, so let's write those down first. So row 1 and row 3 are going to stay the same. What's going to change is row 2. And how is it going to change? Well, we're going to replace the original row 2, which is here, by row 2 plus 6 times row 3. So I did the scratch work here. Here's row 2. Here's 6 times row 3. Here's where row 3 is, multiplying through by 6, 0, 0, 6. And then we add 0, 1, 6 is our new row 2. And so this matrix over here is called the elementary matrix corresponding to the elementary row operation given by this data here. And on the next few slides, we're going to see what benefit considering this matrix is. Let's do one final example. There's an elementary matrix corresponding to multiplying row 2 by 6. And how do we figure out the corresponding elementary matrix? We start with the 3 by 3 identity matrix and perform the corresponding operation, multiplying row 2 by 2, by 6. So this one becomes a 6, and that's exactly what I have here. So this matrix is the elementary matrix corresponding to the elementary row operation consisting of multiplying row 2 by 6. Okay, now how are we going to use these elementary matrices that we've associated to each elementary row operation? And that boils down to this simple fact that given some m by n matrix A, performing an elementary row operation, remember there was 3 of those, 3 types, performing that on A, what do we get? Well, we can express the answer as E times A, where E is the elementary matrix associated to or corresponding to the row operation that we did. Let's do an example to see what's happening. So I start off with some matrix A. It doesn't have to be a square matrix. Here I've chosen one that's 3 by 2. And because the reason I chose it to have 3 rows though is because I want to consider the elementary matrices that are 3 by 3, since that's what I had done on the previous slide. Okay, now let's consider the elementary row operation of switching the first 2 rows. So when we do that to A, well, the 3, 0, 3, 0 and the 1, 2, they just switch positions like so. Okay, now let's see what the matrix multiplication E times A is. Here's E. Remember switching the first two rows, that's our elementary row operation. So we take the identity matrix, switch its rows to get this elementary matrix. We saw this on the previous slide. Then we do E times A. Here's E, here's A. And then when you do the matrix multiplication, well, first of all, we can multiply these two matrices because the first is a 3 by 3, the second is a 3 by 2, and because these numbers match up, we're allowed to multiply them. If those numbers didn't match up, matrix multiplication wouldn't be defined. And then the answer that we get is a 3 by 2 matrix. Okay, so how do we figure out the number in the row 1, column 1 position? Well, we take row 1 of E, dot it with column 1 of A, and then what we see is we get 0 times 1, 1 times 3, 0 times 4, and we get a 3 out of that. And similarly, you can compute all the other positions, and what we see is that when we multiply row 1 times this matrix, the 1 here, which is in the second column, will pick out the second row here, and so that's what will result in row 1 of our answer. Similarly, to get this row, what we'd want to do is take row 2 and multiply it by the columns of this matrix. When we multiply by row 2, because row 2 has a 1 at the beginning, first column, it's going to pick out the first row. And so that's what row 2 of our answer becomes. And that's exactly what the matrix we had over here was. And so here's just a simple illustration of the fact above that performing an elementary row operation on a matrix A is the same as doing this matrix multiplication. Multiplying your matrix A on the left by the elementary matrix associated with the row operation that you're doing. Let's do another example. So this time, let's consider the row operation where we replace row 2 by row 2 plus 6 times row 3. On the previous slide, we saw that this is the corresponding elementary matrix. Here's our matrix A. Again, this A could be any matrix as long as it's 3 by something. And then when we do the matrix multiplication, what we get is this matrix. Let's focus on this second row here. To get this in row 2, I multiply row 2 here with the various columns. And when I take that dot product, I see that 0 times the first row, that's going to be basically ignored, 1 times the second row, plus 6 times this row. And so that's how I get this row 2 here. Here's on this side the arithmetic. Row 2 is 3 and 0 in matrix A. And then 6 times row 3, 6 times 4 is 24, 6 times 5 is 30. I add it and I get 27 and 30, so that's how I got this row 2 here. You can check that 1, 2, and 4, 5 are unchanged. Okay, and so this is the product E times A. And then let's see what happens when we take our original matrix A, I guess it's over here, and replace the second row by, well, row 2 plus 6 times row 3. We computed it here. And so we see that this matrix here and this matrix here are equal. So this provides yet another illustration that performing an elementary row operation is equal, or gives the same answer as when you multiply the matrix you start with on the left by the elementary matrix corresponding to the row operation that you did. Okay, so you might be wondering, well, why are we considering these elementary matrices? And the answer is that they provide a way to find the inverse of a matrix. Now for 2 by 2 matrices, there was a simple formula that we talked about in a previous video. But once you get to 3 by 3 and 4 by 4, there's a formula, but it's not so simple, and sometimes it's just easier to do a procedure involving these elementary matrices to find the inverse. All right, so suppose we have an invertible matrix A. So the inverse exists, and say A is m by m. Then we can do a bunch of elementary row operations to A to get the matrix A in reduced row echelon form. And again, what that meant is that there's zeros above and below the pivot ones. Now, if A is an invertible matrix, that means there is some other matrix so that A times B is equal to the identity, then this reduced row echelon matrix will be the identity matrix. So that's something that for now I'm just going to assert. It's proved more carefully in the book. But let's take that for granted, this fact here for granted right now. And what it translates to in terms of an equation, it's saying that I start with the matrix A and then repeat a bunch of elementary row operations on A. And what we saw in the previous slide is doing row operations on A corresponds to multiplying on the left by various elementary matrices. And if A is invertible, not all matrices are invertible, which again means has an inverse. But provided A is invertible, then doing these elementary row operations, we can get to the identity matrix. Again, the identity matrix is where you have ones along the diagonals and zeros elsewhere. And if you recall the row echelon procedure, you started with a bunch of pivot ones, cleared out the column below it turned into zeros. Then you got another pivot one, cleared out the column underneath it to become 0, and the entries above it to become 0 as well, and so on. And so it's not surprising that for some very nice matrices, namely the invertible matrices, you can get to the identity matrix. Okay, so now the thing to notice, again, the goal is to find a matrix a matrix so that when you multiply by A, you get the identity. And that's exactly what we have here. Let's collect all these elementary matrices. We don't know exactly what they are. It'll depend on example to example. We collect them all, multiply them together into one matrix, and what we see that this equation shows us is that that matrix times A is equal to the identity matrix. And so that means that whatever this matrix is, it's going to be the inverse of A. And so, in other words, just writing down what I said, A inverse is equal to the product of these elementary matrices, and this gives us an algorithm, that means a procedure, to find the inverse of a given matrix A. And this is one key point of the section, is, okay, here's this algorithm. You form, and much like an augmented matrix, but instead of a column vector on the right-hand side, you put the identity matrix here. A, again, is an m by m matrix. And then what you do is do a bunch of elementary row operations to A so that you get the identity matrix here. And as you do the elementary row operations to A, you do the exact same operations to the identity matrix here. And that corresponds to multiplying the matrix you start with, the identity matrix, by a bunch of elementary row operations. By a bunch of elementary matrices corresponding to the elementary row operations that you're doing. And once you end up with the identity matrix here, then you'll end up, whatever matrix you have here will be the inverse. Okay, now that sounds a little hard to follow, so let's do an example. let's start off with a simple 2 by 2 matrix. And remember, we have a formula for finding the inverse of a 2 by 2 matrix. And so if the question was find the inverse of a 2 by 2 matrix, I would use that formula. But because we want to start off with a simple example in seeing how this somewhat complicated elementary matrix procedure works, let's stick with this 2 by 2 matrix. Okay, so we start off with the matrix A on the left, and we put in the 2 by 2 identity matrix. Alright, so then the goal is to turn this into the identity matrix by doing a bunch of elementary row operations. So what we wanted, well, there's a variety of steps you can do. Two different people might come up with two different steps, and the final result of A inverse will be the same, but the intermediate steps could be different. So what I decided to do is divide this entire row by 3, or multiply by 1/3 is what the corresponding elementary row operation is. And the reason I did that is that so I immediately get a pivot 1. So this 3 becomes 1, this 1 becomes 1/3, 1/3, and 0. So this entire row I multiply by 1/3. Okay, so now I have my pivot 1. Again, that's why I multiplied by 1/3, so I get a 1 in this spot. Then what I'm going to do is turn this 5 into a 0 by subtracting 5 times this row from the second row. So the arithmetic is over here. I take row 1, multiply it by -5. So 1 times -5 is -5. Similarly, this -5/3 comes from 1/3 times -5, and so on. And then I'm going to replace row 2 by this plus row 2. So that's what I copied over row 2 over here. Then I'm going to add, doing the arithmetic, I get this row here. So that's going to be my new row 2. So that's what I've copied over here. I've copied 0, 1/3, -5/3, 1 out over here. Okay, so the point is now I've got the 0 here. Next, I want to, again, I'm trying to get 1, 0, 0, 1 here. What I did next is I'm going to take this 1/3 and subtract it, or subtract this entire row 2 from row 1, and replace row 1 by the result. So, okay, so I multiply row 2 by -1 to get this. I'm going to add row 1 to that, and then I get this. And so the point is I have a 0 here. And so that's what our new row 1 becomes. So again, to recap, I'm replacing row 1 by row 1 plus -1 times this, and that will turn this 1/3 into a 0. Okay, so now I've got this matrix here. Sometimes I write the vertical line, sometimes I don't. But okay, and then again, I'm trying to get this into 1, 0, 0, 1 by doing elementary row operations. And now it's fairly easy. I can just multiply this 1/3 by a 3, corresponding to multiplying the entire row by a 3, and that will give me 1, 0, 0, 1 here, the 2 by 2 identity matrix, and then I'm done. And the answer, whatever matrix that's out over here, is the inverse of A. And if you use the formula that we learned last time for A inverse for 2 by 2 matrices, you know that it gives the same as the answer we find here. This is a matrix with determinant 3 times 2 minus 5 times 1, so determinant 1. So we don't have to divide every single entry by the determinant. And so then to find the inverse, you flip the diagonal entries, so 2 and 3, and then put a minus signs on the off diagonal. So that's the quick way. And you might say, well, why then did we have to do all this entire long-winded procedure with a lot of arithmetic to find the inverse if there's a quick formula? Well, the answer is that quick formula is only for 2 by 2 matrices. Next, we'll do an example with 3 by 3 matrices to find the inverse, and there we're going to have to use this, this procedure or algorithm, at least for now. Okay, this is exercise 15 on page 59 of Anton. So the question is, find the inverse of this 3 by 3 matrix. Okay, and then the solution is you form this matrix where you have the original matrix A and the 3 by 3 identity matrix here. And then simply we want to do a bunch of elementary row operations to turn this matrix here into the identity matrix, the 3 by 3 identity matrix. In other words, we've got to get ones along the diagonals and zeros elsewhere. And again, there's multiple ways to do this. There's not a single unique way. And what you see on the slide is just one thing that I did. So the first thing I did was get this 2 to become a 0 by subtracting off this first row. In other words, replace row 2 by row 2 times -1 of the first row. Row 2 is what's going to change. The other rows are going to stay the same, so I can copy them over. 266, 277, so I've copied those over. And then row 2 is, I take the original row 2, and I'm going to add to it -1 times row 1. So -1 times row 1 is computed over here. I do whatever operation involved to the rows of the identity matrix as well. So this one becomes a -1, and then I add. Okay, so -2 and 2 is 0. Here again, I've just copied row 2. Doing the arithmetic, I get this, and this then I copied down over here is my new row 2. So the point was we got a 0 here. So that's closer to the identity matrix than what we originally started with. Okay, then the next thing I want to do is turn this 2 into a 0 by much the same way of replacing row 3 by row 3 plus -1 times row 1. Row 3 is what's going to be replaced. The other two rows, the first and second, they're going to stay the same. So I copied them over from this matrix up here. Then my new row 3, the arithmetic is done over here. I take row 2 and add to it -1 times row 1. I do the arithmetic and I get this. And so I copied that over here. All right, so now I'm getting closer and closer to the identity matrix here. I would want this to be a 0. That would be the next step. And so what I do is replace row 3 by, well, I'm going to use this one as my pivot. And so basically cancel, subtract off, use this one to turn this one into a 0 by replacing row 3 by row 3 times -1 row 2. That's what I had written over here. So here's this row 3 I've copied down here. -1 times row 2. There's a typo here. This should be a 2. And then I do the arithmetic, and I get that this 0, 0, 1, 0, -1, 1 is my new row 3. Okay, so we're getting closer and closer to the identity matrix on this side, and the inverse is slowly being built up on this side. The next row operation I'm going to do is divide this entire row by 2, or in other words, multiply by 1/2. And so that's why this 266 changed to a 133, and this 1 changed to a 1/2. Next, what I'm going to do is use this pivot 1 to turn this 3 into a 0 by replacing row 1 by row 1 plus -3 times row 2. So that's the scratch work on the side over here. I've copied row 1 and multiplied row 2 by -3. So this 1 changed to a -3, -1 and 1 changed to 3 and -3, and then I add, again I'm adding row 1 and -3 times row 2, do the addition, and that's going to be my new row 1. So on the next page, I'll copy this over as our first row. So that's been copied over here. Row 2 and row 3 have also been copied over. And then finally, I almost have the identity matrix here, but I need to return this 3 into a 0, and that's by using this pivot 1 and replacing row 1 by row 1 plus -3 times row 3. So I take row 3, multiply it by -3, so that's here, and I'm adding row 1, do the addition, and then this is a new row 1. That's been copied out over here. And now I have the identity matrix over here, and so that means whatever is on this side must be the inverse of A. And so let's just write that separately. A inverse is this matrix here. So that's our answer.